We are in AP Precalculus. We're doing the note for topic 1.3, rates of change in linear and quadratic functions. All right, I'm reading. For any linear function, the average rate of change over any length input value interval is constant. We often think of this as the, Claire already said it. Say it again, Claire.
Slope?
The slope.
Oh, that was right.
Excellent. All right. Let's move to example 1. The table above gives selected values of the function f of x. Explain why f of x is not a linear function.
Spell my name wrong like 10 times. You're right. You won't let me.
Me? Oh,
Your name?
let me see.
Oh, wait, no. It's just this
Why is
one.
it wrong?
It's just
Oh.
only one. You have,
I didn't write it down. Oh, yeah.
You did?
I wrote the.
It's a Solomon.
That's funny.
All right, so what I need to do here is I need to
I just
analyze our change in x and the change in y. And I'm going to look at the slope because, as it said up here, the slope should be constant. Again, the average rate of change over any length, this is really the slope. The slope over any length should be constant, aka doesn't change. Which means if I find the slope between 4 and 7, and it's a different slope between 7 and 10, something bad has happened. All right, over here, 4 to 7, I add 3. 7 to 10, I add 3. 10 to 13, I add 3. And at first glance, you're like, that's constant, Mr. Sindel. Why is this not constant? Because of the left side.
But it doubles though.
Over here, we add 1. Over here, we add 3. Over here, we add 4.
Oh, yeah, which is double.
My goodness, Mr. Sindel.
Yeah, I get
Log
it.
that shit. Post way install, you get it.
Oh, man, I would just look up.
Which means, again, there are 3 different slopes here. 1, 2, 3 different slopes. We can say this.
Wait, but can you not multiply? Because it's really just times 2.
It is times 2, and when you multiply, that is called exponential. This is not linear. When we're talking, we're just looking for linear, right? Linear means they have to be the same, adding over and over. It's a common difference over and over. So we'll say on the interval between 1 and 2, I meant to do a bracket there. On 1 and 2, the slope is this. The slope is equal to the change in y, which is plus 3, and the change in x was plus 1. But on the next interval, on 2 to 4, the slope is something else. The slope is plus 3 for the y coordinate and plus 2 for the x coordinate. And then furthermore, on 4 to 8, on this interval between 4 and 8, the slope is an entirely different thing. The slope is change in y is 3, change in x is 4. None of those are the same. If any of them are not the same, it is not a linear function. I get a confused face from solve. Are you okay? Raise both hands. You know how to start? Okay.
Why? Yeah.
The definition up here, I'm just using the definition. The definition, the slope doesn't change. The slope here did change, therefore it's not linear. You all nod our heads vigorously. Give me a fist of 5. Give me a little bit more feedback. That makes sense. Perfectly clear. Or not at all.
What are we making
Give
sense
me a
of?
1.
How you got the slope or how?
What, can you explain in your own words why this is not a linear function?
Yeah, I think so.
You're like a 5 or 4? What number out of 5 are you? Anatoly, what do you got?
3.5.
Or it's like, don't tell them. I'm at a 1. I'm seeing a 4, 3, 5. 1, 51. All right. All right, let's look at example 2. Consider the quadratic function g of x is equal to x squared. Complete the table of values for g of x over the consecutive equal length input value intervals below. Okay, we'll do that. And then once we do that, then complete the table for average rates of change of g of x for each consecutive interval of each length input value. Okay, so it's pretty straightforward. Let's go ahead and, this is the squaring function, just take the power of 2. -3 times -3, we all shout out. 9, -1 times -1. Okay, everyone shout out, not just Solomon. He's doing all the heavy lifting. 1, 9, 25. Good, okay. So, what I'm hoping to see over here is that these rates of change, and again, I'm going to.
Oh,
I
it's
see.
a U. That's why I was confused.
It is. This is a quadratic. Yeah. So if you guys want to put this down, whenever you see this word quadratic, that means it's like a smiley face or it's a rainbow. It's one of those U shapes. Good, good, good. What I'm hoping to see here is because this thing was not linear, these numbers should not be the same. We'll see if that's true or not. So let's try it. Between -3 to -1, what was our change in y? We went down 8. So I'm going to do this in a different color. We went from here to here was down 8. So our top of the fraction is -8. And what was the change in x? Did we add or subtract? We added 2.
Go this side. That's what we're doing.
So -8 over +2 is -4. Okay, pretty good, pretty good. What about between -1 and 1? How do I get from 1 to 1? You don't do anything, and from -1 to 1, I add 2. 0 over 2. It'll be 0 over 2, which is just 0. And just right now, you can already tell, okay, that's clearly not linear because these are different slopes, different average rates of change. Yeah, cross off average rates of change and change that to the word slope. All right, let's test another one. How do I get from 1 to 9? I add 8. How do I get from 1 to 3? Add 2. And what do I get here? This is going to be 8 over 2, which is just going to be 4. And finally, 9 to 25, this way, help us out.
9 to 25, okay. 16.
Good, so we're going to add 16. And from 3 to 5, so our slope here is going to be 8. So, done. We completed both tables. That's what it said. But now this is the key question down here. What do you notice about the average rates of change? Nope. We're switching you out. Average rates of change. You are now slopes. What do you notice about the slopes? Over these consecutive equal length input intervals. And when they're different, but more. There's something more. What's going on?
They're like the same. It was negative, and then 0, and 4, and then 8, and then above that would be -8.
Yeah. So if I did like an interval between -5 and 3, or something like that.
Oh, yeah, one above.
Yeah. So if I did -5, comma -3, if I did the one above this, I would probably get a -8. There's this symmetry here. We got the symmetry over the center divider where we crossed the 0 between -1 and 1 was 0. So this symmetry is over here. We have +4, -4, +8, -8. What do you think the next one would be?
16.
It's probably going to be 16. I'm seeing a doubling pattern.
I was gonna say that.
I'm seeing it.
Or it could be a +4 pattern. It could be either one. Because I'm seeing, how do you get from 0 to 4? You get double, right?
Oh, you're right.
Yeah, so maybe it is a +4. It could be 12. But again, it's not asking us to do that. So what I want you to do here is don't rewrite my answer. Write your own answer. First of all, they're different. And I saw symmetry over the interval between -1 and 1. All right, so you have that written down. I kind of want to peek at the answer key over here to see what what Ted got said. Okay, I'm looking at the answer key. Ted said this: the average rates of change over those intervals are increasing by, and he said, and told his answer. He said by +4 each time.
Yeah, that's actually good.
He took his eyes at 16.
Right.
You said 12.
So, Anatoly, definitely have that in your notes. I want to move on to example 3. We've got 14 minutes left. I got time for this. All right. Selected values of various functions are given in the tables below. For each table, determine if the function could be linear, quadratic, or neither. So, what are the defining characteristics of linear? We know that one pretty well.
The first one's 9.
The first one was what?
It's gonna be 12.
Be careful.
It's +1 and then it's +1 +3 +.
You can do multiple.
You're like 2 steps ahead of me. First, I want to define what these look like, and then we can start breaking the definitions. What do we notice about these slopes for linear functions? They're all the same.
Yeah, that's
What do we notice about the slopes for quadratic functions? They constantly increase.
So if it goes times 2 times 3 times 4 times 5, it's not. It's not.
Yeah, I think it's gonna be something else, like exponential or something like that.
What, the first one?
Yeah, that's just.
The first
We'll see.
It can be.
Again, I'm not so sure about the constantly increase because that feels wishy-washy, like constantly increase by like adding, by multiplying. I'm not sure what I mean by that. I want to take a peek at each of these and see what's happening. But let's go ahead. We want to compare slopes. So between 0 and 1, we did +1. Between 1 and 4, we did +3. Between 4 and 9, we did +5. And each of these is +1, +1, +1, which means we don't have to divide by anything. We always divide by the change in x. The change in x in each of these is 1, which means that the denominator of our slope is, we don't have to worry about it.
That's so basic. We're up 1, right 1, right 1.
So I don't know how much I'm supposed to teach you right now. I'm just going to teach you everything I know. What we want to do is look at the second differences. So in this case, the first differences are all random numbers. What I'm going to do now is I'm going to do the difference of the difference. What's the difference between 1 and 3? What's the difference between 3 and 5? 2. Therefore, this thing is quadratic. Yeah. The second difference is constant, aka doesn't change. This one was a constant 2. Then quadratic. And I can give you, I don't know how much information, I don't want to overwhelm you, but quadratic means it's like x to the power of what? X to the power of 2. Did you know that linear is x to the power of 1? Linear had all of the first differences. Yeah, we're gonna know less. So notice this pattern. When we had an x to the power of 1, the first differences were constant. When we had x to the power of 2, the second differences were constant. What do you think would be constant if we had something like x to the power of 3? Not the first differences.
The next one is
-1, I don't know.
Look at the pattern again. I'm trying to make this as the third
I
difference.
said that.
Oh, I didn't hear that. Sorry.
What's the first one?
The third differences are constant, means we have x to the power of 3. The second differences are constant, we have x to the power of 2. If the first differences are constant, it's an x to the power of 1. Cool. Look, and you can see that in our last table. Like, look at this. What is the difference between these two? What's the difference between, oh wait, I don't want to do it that way. I want to do it this way. What's the difference? We did these. What's the difference between -8 and 0? +8. What's the difference between 0 and 8? +8. What's the difference between 8 and 16? +8. This was the second difference. The first difference were all over the place, but the second differences were all constant amounts.
We do a third one?
We don't need to do a third one because we already
No,
done.
but if we do need to do a third one.
You might, but not for this lesson. This lesson is only, it doesn't do cubic, it's only quadratic. Quadratic means x to the power of 2, let me write this up here, means x to the power of 2, which means we only look at the second difference. So far, so good?
it's like 1 over, it's 1, 1, and then it's 3 divided by 5. That's linear though. It's like if we do it, it's just 1, 1, 1.
1, 1.
Because it's the same number. It's
So
the same number on both sides.
You're making up your own table? Tell me the size of your table?
It's the second table.
Oh, the second table? Oh, B? Okay, let's just do it real quick. 0 goes to 1, plus 1, then shout them out. Then, okay, and then we're gonna look at the differences again.
It's the same one.
Okay, therefore this one is, so B is quadratic.
Does the other side not matter?
Oh, shoot.
No, because it's 1 through 5 on the other side, so it's really just 1 and 1. So it is.
It's 1 through 5 and 1 through 5.
That's what I was asking.
That is, no, you're right. I jumped the gun there.
Extra credit.
Yeah.
Okay.
Over here, I did a very good job of being careful. It was +1 + 2. This one, it tricked me. God, Mr. Sindel. This one is not quadratic. Because we have to have a constant over on the left. This one was +1, +3, +5. So this one is actually linear. Because, well, I don't want to give it away. Why is it linear?
Because if you put them together, 1 with 1 is 1, 3 and 3 is 1, 5 is 1.
Exactly. Yeah, the slopes. The slope was 1/1, that's 1. 3/3 is the slope of 1. 5/5 is the slope of 1. All of these have the same slopes, therefore all of them are.
So do you have to put like, never mind.
All right. Ooh, my goodness.
This one's not bad. They're all the same.
Okay, this one is
The
going to be
second difference is
plus
quadratic.
2,
This is not the same.
It's
plus
quadratic.
2, plus 2. This one's going to be plus 2,
It's 2,
plus
1, 0, and then the
1
difference between them all
plus
is 1.
0. Okay, so
It's quadratic.
if these are all the same, then you have permission to look at second
Which
differences.
is good.
It's minus.
-1, -1. Oh, look, the same number. Claire, you got it. Good job. It's quadratic. That's just a natural. Good job. So let me make a note on these. These first and second differences only can be applied if x increases by constant. If you're constantly going up, so in this one we went +2, +2, +2. In this one we went +1, +1, +1. If they're constant, then you can look at first and second differences. This one tricked us and it wasn't constant, so we had to go back to our old definition of just looking at slopes. We saw that all the slopes were the same: 1 divided by 1, 3 divided by 3, and 5 divided by 5. Oh, I'm also supposed to be checking to see if my camera is still working. And it's not. Swivel Screencast Plus has dropped connection. Lovely. Good to know. I think it happens whenever my videos are over 15 minutes. So that's my hypothesis for them. All right, we're almost done because notes are done after this. Yes, no more pages after this. Concave up. The average rate of change over equal length input value intervals is what for all small length intervals? What is this even saying? Let me read this again. The average rate of change, I'm going to swap you out.
It doesn't say rate. It just says the average of change.
Oh, I think that might be a typo on Bryan's part, but maybe it's not. Let me be careful about criticizing. Let's pretend that it's slope. The slope over equal length input values is
Let's tell me we can see this.
0. Sounds about right.
the slope should be increasing. Let's check the answer key. Let's see if I'm right. Slope is increasing. Yeah, I got it right. And this is, I really do need to make a speed sheet for all my AP classes. This is a speed sheet definition. And I'm going to make this as simple as possible. Change this all to just say slope increasing. If you ever see the words slope increasing, it's concave up. 100% of the time. Concave up means slope is increasing. Concave down means, guess what? Slope decreasing. This was coming up on our last worksheet, on worksheet D for topics 1.1 and 1.2. That was the very last homework assignment that we turned in yesterday. There was one question on there that had a question that said slope increasing. Like, we haven't learned this yet, and it happened right now. Slope decreasing, and I should write the word decreasing again over here. That is synonymous with saying concave down. No, yeah. And I think that is a typo there. It should be average rate of change. All right. Now let's look at example 4, and then we can be done with the notes and done for the day. I'm just going to go ahead and say blah, 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 blah. For each function, determine if the function should be concave up, concave down, or neither. Okay, let's go ahead and make sure they're all increasing by the same amount. We're doing plus 0.1, plus 0.1, plus 0.1. This one is constantly increasing, so we can look at the first and second differences to see what's going on.
Then it's +1.
-3, -2, -1. And Solomon jumped ahead of us, and he said that the second differences are +1. So, by the way, I'm using this word differences, but this has another synonym. While this column right here can be called the first differences, it can also be called the slopes. While this column right here can be called the second differences, it can also be called the concavity. If the concavity is positive, then it's concave up and it is a smiley face.
So if it goes negative, it's, the frowny face.
It's a frowny face. I like it being positive, so I switched to rainbow. But yes, you can say frowny face too. All right, let's go ahead and check. We're increasing by, oh wait, do we make a, what do we determine from those second differences? First of all, it's quadratic. Not only is it quadratic,
Oh, we have to write
you
quadratic.
don't, I didn't say that in the instructions, but I just want to go
No, I just wondered.
be an overachiever. Yeah, you're good. It is quadratic, but because it's a constant, but also it's a concave up, down, or neither.
Oh,
It's concave up because those are positive. So just write concave up. Done. All right. So next one, you guys can go through these ahead of me. You don't have to wait for me. I've noticed each of these are increasing by a constant 0.1 no matter
if
what.
it's linear, it's positive, concave up. Oh, it's negative.
Oh, if it's linear, it has no concavity.
Oh, okay.
Again, you look at that second difference. If the second difference is 0, that means the concavity is 0. It has no concavity.
Okay. We're done with the notes.
All right, just compare what you've got to mine. I'm just going to go over this really quickly, and we got like a minute left of class. In part B, we found that this was linear because the first differences were all the same number. They were all constant. And so if it's linear, that means that the second differences are 0, meaning you have no concavity. You could have also written neither. It's also fine. In part C, we found it went, first differences were 6, 4, 2. Second differences were both -2, -2. Second differences is the concavity. Second differences are negative. Negative means we're concave down. And also, because they're the same number, that does mean we are quadratic. We learned a lot that lesson.
That was easy.
I'm glad you think so.
Yeah, this is what-
Well, that's because